Most people look up at the Milky Way and see something permanent. A beautiful collection of 400 billion stars that has been here forever and will be here forever. Our safe, stable home in the universe. But that's not the full story. Right now, multiple threats are bearing down on our galaxy. Some are already happening. One could arrive with absolutely zero warning and erase everything before we even knew it started. And the threat we have been told about for decades, the one that seemed certain, well, recent data is making scientists question if it will happen at all. These are the biggest threats to the entire Milky Way, and we are going to count them down, from terrifying to potentially galaxy-ending. Before we dive into what could destroy or completely transform our galaxy, we need to talk about why this matters right now in 2025. The last few years have been absolutely game-changing for understanding the Milky Way. The James Webb Space Telescope is sending back images and data that are rewriting textbooks. The Event Horizon Telescope just gave us our first direct look at the monster at our galaxy's heart. The Gaia mission has mapped over 1 billion stars with incredible precision. And supercomputers are running simulations that are showing us futures we never imagined. All of this new information is revealing that the Milky Way is far more dynamic, far more vulnerable, and far stranger than we ever thought. It's not just sitting there in space, unchanging. It's evolving, it's under pressure. And yes, it faces real threats. We are going to look at 3 major threats in this documentary. We will count down from number 3 to number 1, and I promise you, each one is going to make you see our galaxy differently. But first, let's talk about what we are actually dealing with here. The Milky Way is not some abstract concept, it's our home. Everything you have ever known, every person who has ever lived, every star you can see with your naked eye, it's all part of this one galaxy. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure made of stars and spiral arms that wind outward from that bar. It is about 100,000 light-years across. To put that in perspective, if you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. Our solar system sits about 26,000 light-years from the center, in a minor spiral arm called the Orion Spur. We are not in the thick of things. We are actually in a relatively quiet suburban neighborhood of the galaxy, which is probably a good thing for life on Earth. Our own position in the galaxy is more significant than it might seem. The Orion Spur places us between 2 major spiral arms, the Perseus arm and the Sagittarius arm. This interarm region is less dense with stars and gas, which means fewer supernova explosions in our immediate vicinity. Supernova are spectacular but deadly events. If one occurred too close to Earth, within about 30 light-years, the radiation could strip away our ozone layer and expose the surface to harmful ultraviolet light. Our orbit around the galactic center is nearly circular, which is also fortunate. Some stars have highly elliptical orbits that take them plunging through dense spiral arms repeatedly. Our stable, circular path keeps us in relatively calm interarm regions for most of our journey. We do occasionally pass through spiral arms, but these transits happen slowly over millions of years. The Sun completes one orbit around the galactic center every 225 to 250 million years. This period is sometimes called a galactic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. The galaxy contains somewhere between 100 billion and 400 billion stars. The exact number is hard to pin down because we cannot see all of them. Dust and gas block our view, especially when we try to look toward the galactic center or through the thick disk. Most of these stars are small, dim red dwarfs that burn their fuel slowly and will outlive our Sun by trillions of years. But there are also massive blue giants that burn hot and bright and die young in spectacular supernova explosions. And there are countless stars like our Sun, medium-sized yellow stars that can support planetary systems for billions of years. Around these stars orbit planets, lots of planets. Recent discoveries have shown us that planets are not rare. Nearly every star has at least one planet, and many have multiple planets. When you do the math, that means there could be hundreds of billions of planets in the Milky Way. Some of those planets are gas giants like Jupiter. Others are rocky worlds like Earth. And a significant number orbit in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface. Our own position in the galaxy is more significant than it might seem. The Orion spur places us between two major spiral arms, the Perseus arm and the Sagittarius arm. This interarm region is less dense with stars and gas, which means fewer supernova explosions in our immediate vicinity. Supernova are spectacular but deadly events. If one occurred too close to Earth, within about 30 light-years, the radiation could strip away our ozone layer and expose the surface to harmful ultraviolet light. Our orbit around the galactic center is nearly circular, which is also fortunate. Some stars have highly elliptical orbits that take them plunging through dense spiral arms repeatedly. Our stable circular path keeps us in relatively calm interarm regions for most of our journey. We do occasionally pass through spiral arms, but these transits happen slowly over millions of years. The Sun completes one orbit around the galactic center every 225 to 250 million years. This period is sometimes called a galactic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. Liquid water is crucial for life as we know it, and the fact that there are potentially billions of habitable zone planets in our galaxy suggests that the building blocks for life are common, even if life itself might be rare. Between the stars exists something equally important: the interstellar medium, a tenuous mix of gas and dust that fills the space between stellar systems. This material is incredibly thin, often just 1 atom per cubic centimeter, far more empty than any vacuum we can create in laboratories on Earth. Yet despite its thinness, there is so much space between stars that it all adds up. The interstellar medium accounts for about 10 to 15% of the galaxy's visible matter. This is where new stars are born. When regions of the interstellar medium get dense enough, gravity begins pulling the gas together. The cloud collapses under its own weight, spinning faster as it contracts, heating up from the compression. Eventually, the core gets hot enough and dense enough that nuclear fusion ignites. A new star is born. The leftover material around that young star can clump together to form planets, moons, asteroids, and comets. This process has been happening for billions of years. Stars are born, they live for millions or billions of years depending on their mass, and then they die. Small stars fade away gently, cooling into white dwarfs. Massive stars explode as supernova, blasting their outer layers into space. Either way, they return their material to the interstellar medium, enriching it with heavy elements created in their cores through nuclear fusion. Those heavy elements are crucial: carbon, oxygen, nitrogen, iron. All the elements heavier than hydrogen and helium, they can only be made inside stars or in supernova explosions. The very first stars in the universe contained almost no heavy elements. They were made of just hydrogen and helium. But those stars lived and died, scattering heavy elements across space. Each new generation formed from gas slightly richer in these elements. Between the stars exists something equally important: the interstellar medium, a tenuous mix of gas and dust that fills the space between stellar systems. This material is incredibly thin, often just 1 atom per cubic centimeter, far more empty than any vacuum we can create in laboratories on Earth. Yet despite its thinness, there is so much space between stars that it all adds up. The interstellar medium accounts for about 10 to 15% of the galaxy's visible matter. This is where new stars are born. When regions of the interstellar medium get dense enough, gravity begins pulling the gas together. The cloud collapses under its own weight, spinning faster as it contracts, heating up from the compression. Eventually, the core gets hot enough and dense enough that nuclear fusion ignites. A new star is born. The leftover material around that young star can clump together to form planets, moons, asteroids, and comets. This process has been happening for billions of years. Stars are born, they live for millions or billions of years depending on their mass, and then they die. Small stars fade away gently, cooling into white dwarfs. Massive stars explode as supernova, blasting their outer layers into space. Either way, they return their material to the interstellar medium, enriching it with heavy elements created in their cores through nuclear fusion. Those heavy elements are crucial. Carbon, oxygen, nitrogen, iron, all the elements heavier than hydrogen and helium, they can only be made inside stars or in supernova explosions. The very first stars in the universe contained almost no heavy elements. They were made of just hydrogen and helium, but those stars lived and died, scattering heavy elements across space. Each new generation formed from gas slightly richer in these elements. But the Milky Way is not just stars and planets. Between the stars, there is gas and dust, what astronomers call the interstellar medium. This material is incredibly thin. In most places, there might be just 1 atom per cubic centimeter. That is a better vacuum than anything we can create in a laboratory on Earth. But there is a lot of space between the stars, so all that thin gas and dust adds up. In total, the interstellar medium accounts for about 10 to 15% of the visible matter in the galaxy. And it is crucial because this is where new stars are born. When regions of the interstellar medium get dense enough, gravity starts to pull the gas together. The cloud collapses, heats up, and eventually ignites nuclear fusion. A new star is born. And the leftover material around that star can clump together to form planets. This process has been happening for billions of years. Stars are born, they live for millions or billions of years depending on their size, and then they die. Small stars fade away gently. Massive stars explode. Either way, they return their material to the interstellar medium, enriching it with heavy elements that were created in their cores. Those heavy elements, things like carbon, oxygen, nitrogen, iron, they are crucial for planets and for life. The very first stars in the universe contained almost no heavy elements. They were made of just hydrogen and helium, the 2 lightest elements. But those stars lived and died, and their explosions scattered heavy elements across space. Each new generation of stars formed from material that was a little bit richer in heavy elements. Our Sun is at least a 3rd-generation star, possibly more. It formed from a cloud that already contained all the elements needed to make rocky planets and eventually life. So when we talk about threats to the Milky Way, we are not just talking about threats to a collection of stars. We are talking about threats to the entire ecosystem that makes our existence possible. The structure of the galaxy, the distribution of stars and gas, the central black hole, the interactions with other galaxies, all of it plays a role in creating the conditions where life can emerge. And now, with our modern telescopes and instruments, we are learning that this ecosystem is far less stable than we thought. The galaxy faces real challenges. Some are slow and gradual. Others could be sudden and catastrophic. Let's start with the most terrifying one, even though it is also the least likely. This is the threat that keeps theoretical physicists awake at night, even though the chances of it happening are vanishingly small. It is called false vacuum decay, and if it happens, the Milky Way would not just be destroyed. It would be erased from existence faster than you could blink. To understand this threat, we need to talk about quantum field theory, but I am going to explain it in a way that makes sense without needing a physics degree. Think about energy states. Everything in the universe wants to be in the lowest possible energy state. It is like a ball rolling down a hill. The ball naturally moves downward until it reaches the bottom, and then it stays there because that is the most stable position. In physics, we call the lowest possible energy state the true vacuum. It is the ground state, the bottom of the hill. When something is in the true vacuum, it is as stable as it can possibly be. It is not going anywhere. But here is where it gets interesting. Imagine that ball is not sitting at the very bottom of the hill. Instead, it is sitting in a small dip on the side of the hill. From the ball's perspective, it looks like it is in a stable position. It is not rolling anywhere, but technically there is a lower position further down the hill. That small dip is what physicists call a false vacuum. It looks stable, and it can stay stable for a very long time, but it is not the true lowest energy state. The ball could, in theory, escape that dip and roll down to the actual bottom of the hill. Now, apply this idea to the entire universe. The universe might be sitting in a false vacuum right now. All the forces of nature, all the particles, all the physical laws we observe, they might be based on a universe that is not in its true lowest energy state. To understand why this matters, we need to think about what vacuum actually means in physics. When most people hear the word vacuum, they think of empty space. A region with no air, no matter, nothing at all. But in quantum physics, vacuum is not empty. It is actually the lowest energy state of a quantum field. This is one of the strangest predictions of quantum mechanics. Even in completely empty space, with no particles and no matter, quantum fields are still there. They are always present, filling all of space. And these fields have energy, even in their ground state. You can think of these quantum fields like the surface of an ocean. Even on a calm day, the surface is not perfectly flat. There are always small ripples and waves. In quantum field theory, these ripples are particles. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field, and so on. The vacuum is the state where the field has the lowest possible energy, but it is not zero energy. There is still something there, still activity at the quantum level. Particles can spontaneously appear and disappear in what are called quantum fluctuations. They borrow energy from the vacuum, exist for a tiny fraction of a second, and then vanish again. This has been experimentally verified. These quantum fluctuations create measurable effects, like the Casimir effect, where two metal plates placed very close together in a vacuum will be pushed together by the quantum fluctuations in the space around them. So the vacuum is not nothing. It is a quantum field in its lowest energy state. And the question is, are we sure that the vacuum we are in right now is the true lowest energy state? Or could there be an even lower state that we have not fallen into yet? This is where the false vacuum idea comes from. If our current vacuum is not the true ground state, then it is metastable. It looks stable. It can persist for an incredibly long time, but it is not absolutely stable. Under the right conditions, it could transition to the true vacuum. And that transition would change everything. Everything seems stable. Physics works the way we expect it to work. Atoms hold together, stars shine, galaxies rotate. But if the universe is in a false vacuum, there is a lower energy state out there, and we just have not fallen into it yet. So what would make us fall into the true vacuum? This is where quantum mechanics comes in. At the quantum level, particles can do weird things. One of those weird things is called quantum tunneling. Basically, a particle can sometimes appear on the other side of a barrier without actually having enough energy to climb over that barrier. It is like if you were standing in front of a wall and suddenly, randomly, you found yourself on the other side without climbing over it or going through a door. Quantum tunneling is well documented. We see it happen in laboratories all the time. It is one of the strange but real consequences of quantum mechanics. To understand tunneling better, think about it this way. In classical physics, if you throw a ball at a wall, the ball either has enough energy to go over the wall or it does not. If it does not have enough energy, it bounces back. Simple. But in quantum mechanics, particles behave differently. They are not solid little balls with definite positions. They are described by wave functions, which give you the probability of finding the particle in a particular location. And here is the key thing. Wave functions do not stop abruptly at barriers. They decay exponentially, which means there is a small but non-zero probability that the particle could be found on the other side of the barrier, even if it did not have enough energy to classically go over it. This probability is usually very small. For large objects like baseballs and walls, it is so incredibly tiny that you would never see it happen. But for subatomic particles and thin barriers, tunneling happens all the time. In fact, tunneling is essential for many processes in nature. The sun shines because of quantum tunneling. In the sun's core, hydrogen nuclei are being fused together to form helium. But for fusion to happen, the hydrogen nuclei need to get very close together, close enough for the strong nuclear force to bind them. The problem is that hydrogen nuclei are positively charged, and like charges, repel each other. There is an energy barrier, an electrostatic repulsion that keeps them apart. Classically, the hydrogen nuclei in the sun's core do not have enough energy to overcome this barrier. But quantum mechanically, they can tunnel through it. The nuclei get close enough that there is a small probability they will suddenly find themselves on the other side of the barrier, close enough for the strong force to grab them and fuse them together. Without quantum tunneling, the sun would not shine, stars would not work, and we would not be here. So tunneling is real, it is well understood, and it happens all the time at the subatomic level. Now, apply this to the vacuum. If the universe is in a false vacuum, sitting in that shallow dip on the side of the hill, quantum tunneling provides a way to escape. Somewhere, at some random point in space, a tiny region of the quantum field could tunnel through the energy barrier, separating the false vacuum from the true vacuum. Just a tiny bubble, smaller than an atom, where the field has spontaneously transitioned to the lower energy state. And once that bubble exists, the physics changes dramatically. Now, if the universe is in a false vacuum, there is a tiny, tiny chance that somewhere, at some random point in space, a small bubble of true vacuum could spontaneously appear through quantum tunneling. Just a little bubble, maybe smaller than an atom, where the universe has fallen into its true lowest energy state. And once that bubble exists, physics changes everything. Inside that bubble, the fundamental constants of nature would be different. The Higgs field, which gives particles their mass, might have a different value. The strengths of the fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, they might all be different. With different force strengths and different particle masses, atoms would not be able to form in the same way. The chemistry that makes stars, planets, and life possible would not work. But it does not just sit there. The bubble starts expanding at the speed of light. Here is why. The boundary between the false vacuum and the true vacuum is a region of incredibly high energy density, like the surface tension of a soap bubble. That boundary wants to minimize its surface area by expanding. The expansion is not driven by any physical object moving outward. It is the vacuum itself changing state, and this transition happens at the maximum possible speed. Here is the truly terrifying part. Because the bubble expands at light speed, we would never see it coming. When we look at distant stars and galaxies, we are seeing the past because light takes time to travel. This is why we can usually see warning signs for cosmic threats. A nearby star about to go supernova shows changes in brightness first. An asteroid heading toward Earth can be spotted years in advance. But with vacuum decay, the light carrying information about the bubble travels at exactly the same speed as the bubble itself. No advance warning, no signal arriving ahead of it. One moment, everything is normal. The next moment, the bubble wall passes through, the fundamental forces change, and atoms simply dissolve. Not destroyed in an explosion, just transformed into a state where matter cannot exist. The Milky Way, Andromeda, every galaxy in the observable universe would be gone, replaced by a new kind of vacuum where our physics does not apply. And it could already be on its way from somewhere distant in the universe, with no possible way for us to know. Now, before you panic, I need to be very clear about the probability here. The chances of this happening are extraordinarily low. Physicists have run calculations based on what we know about particle physics and quantum field theory, and the current models suggest that the universe is either in a true vacuum already or in a false vacuum that is stable enough that decay is incredibly unlikely over timescales far longer than the current age of the universe. The universe is about 13.8 billion years old. If false vacuum decay was likely to happen, it probably would have happened already somewhere in the observable universe. The fact that we are still here and that we see distant galaxies that are billions of years old still existing is pretty good evidence that vacuum decay is not something we need to worry about on any reasonable timescale. But the possibility is not zero. That is what makes it philosophically interesting. The stability of the vacuum depends on something called the Higgs field. You have probably heard of the Higgs boson, the particle that was discovered at CERN in 2012. The Higgs boson is a ripple in the Higgs field, and the Higgs field is what gives particles their mass. When physicists measured the mass of the Higgs boson, they found it was about 125 billion electron volts. That measurement, combined with the mass of another particle called the top quark, tells us about the stability of the Higgs field and therefore the stability of the vacuum. Based on the current measurements, the Higgs field appears to be in what physicists call a metastable state. It is not perfectly stable, but it is stable enough that decay is extremely unlikely over timescales much longer than the age of the universe. Think of it like this. The universe is like a house built on the slope of a volcano. The volcano has not erupted in millions of years. All the geological data suggests it will not erupt for millions more years. But technically, it could erupt tomorrow. You cannot put the probability at exactly zero. That is where we are with false vacuum decay. The house is comfortable. The odds are overwhelmingly in our favor. But the possibility exists, and if it happens, there is nothing anyone could do about it. Some physicists have even asked whether high-energy particle collisions could trigger vacuum decay. When the Large Hadron Collider was being built, there was some concern. Could we accidentally create a bubble of true vacuum and destroy the universe? The answer is no, and here is why. Cosmic rays are high-energy particles from space that slam into Earth's atmosphere all the time. Some of these cosmic rays have far more energy than anything the Large Hadron Collider can produce. They have been hitting Earth for billions of years. If high-energy collisions could trigger vacuum decay, it would have happened already. The fact that we are still here means we are safe. Cosmic rays have been running this experiment naturally for billions of years, and the universe has not collapsed yet. But the theoretical possibility remains. Somewhere in the universe, at some random point in space, a quantum fluctuation could create a bubble of true vacuum. That bubble would expand at the speed of light, and everything in its path would be annihilated. The Milky Way, Andromeda, every galaxy in our local group, every galaxy in the observable universe, all gone. Replaced by a new vacuum with different laws of physics where atoms might not even be able to form. It is the ultimate existential threat, not a physical object we could deflect or avoid, not an event we could see coming, just the fundamental instability of reality itself. But again, the probability is so low that most physicists do not lose sleep over it. It is theoretically possible, but practically irrelevant. So that is threat number 3. False vacuum decay, the bubble of death, the instant eraser, vanishingly unlikely, but truly unstoppable if it ever happens. Now let's move on to something that is not theoretical at all. Something that is happening right now, 26,000 light-years away, at the very heart of our galaxy. At the center of the Milky Way, there is a monster, a supermassive black hole with a mass of about 4 million times that of our Sun, compressed into a region smaller than the orbit of Mercury. We call it Sagittarius A star, pronounced Sagittarius A star, named after the constellation Sagittarius, where it appears in our sky. For most of human history, we had no idea it was there. We could not see the galactic center because thick clouds of dust and gas block visible light from reaching us. But in the 1970s and 1980s, astronomers started using radio telescopes to peer through the dust. They detected a strong radio source right at the center of the galaxy. They called it Sagittarius A star, and they suspected it might be a black hole, but they could not prove it. The proof came from watching the stars near the galactic center. 2 teams of astronomers, one led by Reinhard Genzel in Germany and another led by Andrea Ghez in California, spent decades tracking individual stars as they orbited the invisible center of the galaxy. This was extraordinarily difficult work. The galactic center is 26,000 light-years away. At that distance, even with the best telescopes, individual stars appear as tiny points of light. To track their motions, the astronomers had to take images year after year, precisely measuring each star's position to within a tiny fraction of an arcsecond. An arcsecond is 1/3600th of a degree. To give you perspective, the full moon in the sky is about half a degree across. An arcsecond is 1/1800th the width of the moon. The precision required to track stars at the galactic center is like being able to spot a tennis ball on the moon. And the astronomers did not just need to measure positions, they needed to track how those positions changed over time to determine the star's orbits. This required decades of patient observation. But the results were spectacular. These stars were moving incredibly fast. One star in particular, called S2, completes an orbit around the galactic center in just 16 years. That might sound like a long time, but remember, the Sun takes 225 million years to orbit the galactic center. S2 is orbiting more than 14 million times faster. At its closest approach to the central object, S2 is moving at about 5,000 kilometers per second. That is almost 2% of the speed of light. At that speed, you could travel from Earth to the Moon in less than 80 seconds. The only thing that could make a star move that fast is an incredibly massive object with an incredibly strong gravitational pull. By measuring S2's orbit precisely, along with the orbits of several other stars near the galactic center, the astronomers calculated that the central object had to be about 4 million times the mass of the Sun. And it had to be small. If that mass was spread out over a large region, the orbits would be different. The precise shape of S2's orbit, which is a highly elongated ellipse, told the astronomers that all that mass had to be compressed into a region no bigger than our solar system, roughly the distance from the Sun to Neptune. The only thing that fits those requirements is a black hole. Not a stellar mass black hole, which forms when a massive star collapses at the end of its life, but a supermassive black hole. An object millions of times more massive than the Sun, compressed into a region small enough that the escape velocity exceeds the speed of light. In 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for their work, proving that a supermassive black hole sits at the heart of the Milky Way. It was one of the most important astronomical discoveries of the century, confirming decades of theoretical predictions. But the story does not end there. In fact, it was just the beginning. Because once we knew for sure that Sagittarius A star was a black hole, the next step was to actually see it. Now, to be clear, you cannot actually see a black hole directly. By definition, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole beyond which nothing can escape is called the event horizon. Once anything crosses the event horizon, it is gone forever, pulled inexorably toward the central singularity. So the black hole itself is invisible. It is a perfect black sphere in space, emitting no light and absorbing everything that comes near it. But matter falling toward a black hole does not just disappear quietly. As gas and dust spiral inward, they form what is called an accretion disk, a swirling disk of material orbiting the black hole at incredible speeds. The material in the accretion disk gets compressed as it spirals inward. Compression heats it up, and as it heats up, it starts to glow. The closer the material gets to the black hole, the faster it is moving and the hotter it gets. Very close to the event horizon, the material can be heated to millions of degrees. At those temperatures, it emits X-rays and gamma rays, the most energetic forms of light. The accretion disk around a black hole is one of the brightest objects in the universe, powered not by fusion like a star, but by gravity, by matter falling into an inescapable pit. The Event Horizon Telescope, which is not a single telescope, but a network of radio telescopes spread across the entire Earth, was designed to image this glowing material around black holes. By combining data from telescopes on different continents, the EHT creates an effective telescope the size of the planet, with resolution sharp enough to see details at the event horizon. In 2019, the EHT released its first image, and it was spectacular. They imaged the supermassive black hole at the center of the M87 galaxy, a giant elliptical galaxy about 54 million light-years away. That black hole is more than 6 billion times the mass of the Sun, and the image showed exactly what physicists predicted. A bright ring of glowing material surrounding a dark central circle, the shadow of the black hole itself. In 2022, the EHT released a second image, this time of Sagittarius A star, our own galactic center, our own black hole. The image showed the same features: a bright ring of glowing gas, orange and yellow in the false color image, surrounding a dark central region, the shadow of the black hole. Seeing that image was extraordinary. It confirmed everything we thought we knew about Sagittarius A star. It is real, it is massive, and it is right there at the heart of our galaxy. But imaging Sagittarius A star was much harder than imaging the M87 black hole, even though Sagittarius A star is much closer. The problem is that Sagittarius A star is much smaller. Remember, it is only 4 million times the mass of the Sun compared to 6 billion for M87, and the size of a black hole's event horizon is proportional to its mass. This means Sagittarius A star is over 1,000 times smaller than M87, and because it is smaller, the material in the accretion disk orbits much faster. Gas that takes weeks or months to orbit M87 completes an orbit around Sagittarius, a star, in just minutes. This makes the image of Sagittarius A star change rapidly. Over the course of an observing session, which lasts several hours, the pattern of bright spots in the accretion disk shifts dramatically. It is like trying to take a portrait photograph of a small child who will not sit still. The EHT team had to develop new techniques to deal with this. They could not just take a single long exposure like they did for M87. Instead, they had to take many short exposures and then average them together in clever ways, accounting for how the image was changing over time. The fact that they succeeded is a testament to the incredible skill of the astronomers and engineers working on the project, and the image they produced is one of the most important scientific images of the 21st century. Now, I need to be very clear about something. Sagittarius, a star, is not an immediate threat to us. We are 26,000 light-years away. That is incredibly far. The black hole's gravity does not reach us in any meaningful way. Earth is not going to get sucked into the black hole. The sun is not going to fall in. We are safe, at least from direct gravitational effects. But that does not mean Sagittarius A star is harmless, because the black hole is not just sitting there quietly. It is active, it is feeding, and it has the potential to wake up in a much more dramatic way. The latest observations from the James Webb Space Telescope and the Event Horizon Telescope show that the black hole is far more active than we realized. It is not just sitting there quietly, it is flaring constantly. These flares are bursts of infrared light and X-rays that happen when small amounts of gas fall toward the black hole. As the gas spirals inward, it heats up to millions of degrees and releases energy. Then it crosses the event horizon and disappears forever. The Event Horizon Telescope has also measured something fascinating. Sagittarius A star is spinning, and it is spinning fast. A spinning black hole is different from a non-spinning one. The spin drags space and time around with it, creating what physicists call frame dragging. And a spinning black hole can store enormous amounts of energy in its rotation. The magnetic fields around Sagittarius A star are twisted and stretched by this rotation. The Event Horizon Telescope was able to map these magnetic fields by looking at the polarization of the light from the glowing material around the black hole. What they found is that the magnetic fields are incredibly strong and incredibly organized. They are not random, they are structured, spiraling around the black hole like the threads of a screw. These magnetic fields play a crucial role in how the black hole feeds. They can channel material toward the black hole or fling it away in powerful jets, and that brings us to the real threat. Right now, Sagittarius A star is relatively quiet. It is consuming matter at a slow, steady rate. It is sipping gas from its surroundings, not gulping it down. But it was not always this calm. About 2 million years ago, the black hole went through a period of intense activity. We know this because we can still see the evidence today. High above and below the galactic plane, stretching for 25,000 light-years in each direction, are two enormous structures called the Fermi bubbles. These are huge lobes of high-energy gamma rays, the most energetic form of light. The Fermi Gamma Ray Space Telescope discovered these bubbles in 2010, and they are extraordinary. Each bubble is about 25,000 light-years tall and 15,000 light-years wide. They are so large that they extend well beyond the visible disk of the galaxy. The only explanation that makes sense is that these bubbles were created by a massive energy release from the galactic center about 2 million years ago. Either Sagittarius A star went through a period of intense feeding, consuming a large gas cloud, or a star wandered too close and was torn apart by tidal forces. When that happened, the black hole did not just pull matter in. it also blasted energy outward in powerful jets. These jets shot out perpendicular to the galactic disk, inflating these enormous bubbles of hot gas and high-energy particles. 2 million years later, those bubbles are still glowing. They are still hot. They are still expanding slowly. They are the scars of an ancient outburst. And here is the thing. This could happen again. If another large gas cloud drifts too close to Sagittarius A star, or if another star wanders into the danger zone, the black hole could wake up. It could transition from its current quiet state into what astronomers call an active galactic nucleus. When that happens, Sagittarius A star would become a quasar. It would start shining brighter than all the stars in the galaxy combined, powered by matter spiraling inward at near light speed and heating up to tens of millions of degrees. A quasar at the center of the Milky Way would be spectacular and terrifying. The galactic core would blaze with light across the entire electromagnetic spectrum. Jets of radiation and charged particles would shoot out along the black hole's rotation axis, potentially extending for thousands of light years. And if we happen to be anywhere near those jets, it would be catastrophic. Gamma rays and X-rays would flood the inner regions of the galaxy. Any planets in the path of those jets would be bathed in deadly radiation. Atmospheres would be stripped away. The surface of any world in the direct line of fire would be sterilized. Now we are probably safe. We are far from the galactic center, and the jets would likely be directed perpendicular to the galactic disk, shooting up and down rather than outward through the spiral arms where we live. But even if we are not in the direct path of the jets, a quasar outburst would change the galaxy in profound ways. The radiation pressure from the quasar could blow gas out of the central regions of the galaxy. This would shut down star formation near the core. No new stars would be born in the inner galaxy because all the gas, the raw material needed to make stars, would be blasted away. The energy from the quasar could also heat up the entire galactic disk, changing its structure and potentially triggering or suppressing star formation in different regions. And the black hole itself would grow. Every bit of matter that falls past the event horizon adds to the black hole's mass. Over millions of years of sustained feeding, Sagittarius A star could double or triple in size. Some of the most massive black holes in the universe, the ones that are billions of times the mass of the Sun, probably grew through exactly this kind of sustained feeding. They transitioned into quasars and stayed in that state for millions or even hundreds of millions of years, gorging on gas and growing larger and larger. Our black hole is currently on the small side for a supermassive black hole. The monster at the center of the M87 galaxy, the one that the Event Horizon Telescope imaged in 2019, is over 6 billion times the mass of the Sun. More than 1,000 times more massive than Sagittarius A star. Why are some black holes so much bigger? We do not fully understand. It probably depends on how much gas was available in the early universe, how many galaxy mergers occurred, and how long the black hole has been feeding. But the fact remains, Sagittarius A star has the potential to grow much, much larger than it currently is, and as it grows, its influence on the galaxy would increase. The region immediately around Sagittarius A star is already one of the most extreme environments in the galaxy. Stars there are packed together millions of times more densely than in our neighborhood. They orbit the black hole at incredible speeds. S2, the star I mentioned earlier, has been tracked for over 25 years now. Astronomers have watched it complete more than one full orbit. And during its closest approach to the black hole, something interesting happens. Time slows down for S2. This is a prediction of Einstein's theory of relativity. The closer you get to a massive object, the slower time runs relative to an observer far away. And when S2 swings close to Sagittarius A star, it experiences measurable time dilation. Astronomers were able to detect this by measuring the wavelength of light from S2. As the star dove toward the black hole, the light was redshifted, stretched to longer wavelengths, exactly as Einstein predicted. It was a beautiful confirmation of general relativity, tested in one of the most extreme environments in our galaxy. But not all stars are as lucky as S2. Some stars get too close and are torn apart. When a star wanders within a certain distance of a black hole, the difference in gravitational pull between the near side of the star and the far side becomes so large that it overcomes the forces holding the star together. The star gets stretched like taffy in a process called spaghettification. Eventually, the star is torn apart completely. Its material forms a long stream that wraps around the black hole. As this material falls inward, it heats up and releases a huge burst of energy in what is called a tidal disruption event. Astronomers have observed tidal disruption events in other galaxies, and they are spectacular. The dying star briefly outshines everything else in the galaxy's core. The burst of light can last for weeks or months as the stellar material spirals inward and is consumed. If a tidal disruption event happened at Sagittarius A star, we would see it. The galactic center would suddenly brighten dramatically across multiple wavelengths. It would be an amazing event to witness. And the chances of it happening are not that low. The galactic center is crowded with stars. Tidal disruptions probably happen every 10,000 to 100,000 years. On human timescales, that is rare. But on cosmic timescales, it is fairly common. We could witness one in our lifetimes. Or it might happen 1,000 years from now. Or it might have happened 1,000 years ago, and the light is on its way to us right now. There is also something very strange happening near Sagittarius A star. Astronomers have identified a cluster of young, massive stars orbiting very close to the black hole, within a light year of the event horizon. This is weird because stars should not be able to form that close to a supermassive black hole. The tidal forces are too strong. Any gas cloud that tried to collapse into a star would be torn apart before it could finish forming. So how did these young stars get there? One theory is that they formed farther out and then migrated inward through gravitational interactions with other stars. Another theory is that they formed in a massive disk of gas that briefly existed around the black hole millions of years ago, when the black hole was feeding more actively. We do not know the answer yet, but these stars are there, and some of them are doomed. They are in unstable orbits, and over the next few million years, some of them will spiral inward and be consumed by the black hole. When that happens, Sagittarius A star will flare, it will brighten, it will feed, and the galaxy will change, even if just slightly. This is the nature of the threat. Sagittarius A star is not a bomb waiting to go off. It is a dynamic, active black hole that is constantly interacting with its environment. It flares, it feeds, and occasionally it erupts. The latest data from the James Webb Space Telescope and the Event Horizon Telescope shows that we are living with an active monster at the heart of our galaxy. It is not sleeping, it is not dormant. It is just resting between meals. And when it wakes up, when it transitions into a full quasar state, the Milky Way will change. The inner regions might be sterilized. Star formation might shut down. The structure of the galaxy might be altered. We are probably safe out here in the suburbs, 26,000 light-years away. But the threat is real, it is ongoing, and it could manifest at any time. So that is threat number 2. Sagittarius, a star. The monster at the heart of the Milky Way, not sleeping, just waiting. Now let's talk about the number 1 threat, the one we have been told about for decades, the one that seemed absolutely certain, the Andromeda collision. Except, it turns out, it might not happen the way we thought. For as long as I can remember, Astronomers have been telling us the same story. In about 4 to 5 billion years, the Andromeda Galaxy is going to collide with the Milky Way. The two largest galaxies in our local group will smash together in a spectacular cosmic merger, and the result will be a single giant elliptical galaxy. This has been presented as a certainty. The evidence seemed rock solid. Andromeda is moving toward us at about 110 kilometers per second. That is about 250,000 miles per hour. We have measured this speed using the Doppler shift of Andromeda's starlight. When an object is moving toward you, the light it emits gets compressed to shorter wavelengths, shifted toward the blue end of the spectrum. Andromeda is blue shifted. It is coming toward us. And at that speed, simple math tells you it will reach us in about 4 billion years. Except there is a problem with that simple calculation. It only accounts for one component of Andromeda's motion, the motion toward or away from us, called the radial velocity. But galaxies move in 3 dimensions. Andromeda is not just moving toward us, it is also moving sideways, perpendicular to our line of sight. That sideways motion is called the tangential velocity, and it is much, much harder to measure. To measure tangential velocity, you need to track an object's position in the sky over many years and see how it moves. For something as far away as Andromeda, which is about 2.5 million light-years distant, the sideways motion is incredibly small. We are talking about tiny fractions of an arcsecond per year. For decades, we simply could not measure Andromeda's tangential velocity accurately enough. So astronomers made assumptions. They assumed Andromeda was heading pretty much straight for us, or close to it. But assumptions are not measurements. And in the last few years, we have finally gotten the measurements. The Hubble Space Telescope, using its incredible precision, tracked the positions of stars in Andromeda over multiple years. The Gaia mission, which is mapping the positions and motions of billions of stars in our own galaxy, has also contributed data on nearby galaxies, including Andromeda. And what these measurements show is that Andromeda has a significant tangential velocity. It is not heading straight for us. It is approaching at an angle. What does that mean? It means the collision might not be a direct, head-on smash. It could be a grazing encounter. Or, in the most extreme interpretation of the data, it could even be a near miss. Now, before we go too far, let me be clear. The most likely scenario is still a collision. The data still points toward a merger happening at some point. But the exact nature of that collision, when it happens, how violent it is, and what the final result looks like, all of that is now uncertain. This is huge. This changes the entire narrative we have been told for decades. Let me walk you through the different possible scenarios based on the latest data. Scenario 1, the direct collision. This is still the most probable outcome, but it is no longer a certainty. In this scenario, Andromeda and the Milky Way approach each other on a nearly head-on trajectory. As they get closer, their gravitational fields start interacting. Even when the galaxies are still millions of light-years apart, they can feel each other's gravity. Tidal forces start to distort both galaxies. Stars on the outer edges of each galaxy get pulled toward the other galaxy. Long streams of stars begin to form, stretching between the two spirals like cosmic bridges. The first pass through is spectacular. The two galaxies interpenetrate. Their disks pass through each other. Now, here is something important. When galaxies collide, individual stars almost never actually hit each other. Space is vast, and stars are tiny. Think of it like this. If the sun were the size of a grain of sand, the nearest star would be about 4 miles away. Even when two galaxies merge, there is so much empty space that the stars just pass by each other. But the gas clouds are a different story. When giant molecular clouds from two galaxies collide at hundreds of kilometers per second, they slam together. The collision compresses the gas, heats it up, and triggers massive bursts of star formation. During a galactic collision, the rate of star formation can increase by a factor of 10 or even 100. Millions of new stars are born in a relatively short period of time. The colliding galaxies light up with brilliant blue light from all these hot, young stars. After the first pass, the galaxies do not just merge immediately. They separate, but they are now gravitationally bound. Over the next few 100 million years, they swing back toward each other and collide again and again. Each collision strips away more energy from their orbits, bringing them closer together. Meanwhile, the two central black holes begin their own dance. Sagittarius A star, our 4 million solar mass black hole, and Andromeda's central black hole, which is about 50 million solar masses, start spiraling toward each other. This is a slow process. Black holes do not just crash together, they orbit each other, gradually losing energy by emitting gravitational waves. As they get closer, the orbit speeds up and the gravitational waves get stronger. Eventually, after millions of years, the two black holes merge in a spectacular event that releases more energy than all the stars in both galaxies combined. The merger produces a burst of gravitational waves that would be detectable by any civilization with the right instruments anywhere in the universe. The final merged black hole would be about 54 million times the mass of the Sun, and it would settle into the center of the new merged galaxy. That merged galaxy would be a giant elliptical. The beautiful spiral structures of both the Milky Way and Andromeda would be gone, dissolved by the chaos of the collision. Stars would be distributed in a roughly spherical or football-shaped pattern with no remaining spiral arms. Astronomers have nicknamed this merged galaxy Milky Way. It is a playful name, but it represents a profound transformation. The Milky Way, as we know it, would no longer exist. This is the classic scenario, the one we have been told about for decades, and it is still possible, but it is not certain. Scenario 2, the grazing encounter. Now, let's consider what happens if Andromeda's tangential velocity is high enough that we do not hit head-on. In a grazing encounter, the galaxies still interact gravitationally. They still approach each other. But instead of interpenetrating fully, they swing past each other, like two dancers in a cosmic waltz who come close but do not fully embrace. Tidal forces still rip stars away from both galaxies. Long tidal tails still form, streams of stars stretching across millions of light years. Some stars are flung out into intergalactic space, never to return. Others are captured by the other galaxy. Gas clouds still collide, but not as intensely as in a direct collision. There would still be bursts of star formation, but they would be more localized, concentrated in the regions where the two galaxies came closest. The central regions of both galaxies might remain mostly intact, especially if the closest approach distance is large enough. After the first encounter, the galaxies separate, but gravity does not let them go. Over hundreds of millions of years, their orbits decay. They swing back for another pass, and another. Each encounter strips away more stars, creates more tidal tails, and brings the galaxies closer to an eventual merger. But here is the key difference. In a grazing scenario, the merger takes much longer. Instead of 4 to 5 billion years until complete merger, it might take 10 billion years or more. And during that extended time, parts of both galaxies might survive in recognizable form for much longer than we thought. The spiral structure might persist through the first few encounters, gradually dissolving over billions of years rather than being destroyed in a single violent collision. This scenario changes the timeline dramatically. It means the Milky Way as a spiral galaxy might exist for twice as long as we thought. Scenario 3. The near miss. This is the least likely scenario, but it is now on the table as a possibility. What if Andromeda's tangential velocity is high enough that the galaxies do not actually collide at all on the first pass? In this case, Andromeda would swing by the Milky Way at a distance of perhaps hundreds of thousands of light-years. The gravitational interaction would still be significant. Both galaxies would be disturbed. Tidal forces would create waves in the galactic disks. Some stars would be pulled into new orbits. But there would be no major collision, no intense starburst, no merger of the central black holes, at least not yet. Instead, Andromeda would continue on its trajectory, and the Milky Way would continue on its own. The two galaxies would be gravitationally bound to each other, orbiting around their common center of mass over billions of years. Eventually, over enough time, gravitational interactions would bring them back together. But that final merger might be pushed back by billions of years. We are talking about 10 billion years or more into the future. By that time, our Sun will be long dead. The Sun is currently about 4.5 billion years old, and it has about another 5 billion years of life left. In about 5 billion years, it will swell into a red giant, expanding to perhaps the orbit of Earth or beyond. The inner planets will be engulfed. Earth will either be vaporized or left as a charred, lifeless rock orbiting a bloated, dying star. Then the Sun will shed its outer layers in a planetary nebula and collapse into a white dwarf, a dense remnant about the size of Earth, but with a mass comparable to the Sun. So, in the near-miss scenario, the Milky Way as we know it might actually outlive our entire solar system. The Sun will die before the galaxy merges with Andromeda. What does this mean? The uncertainty in Andromeda's trajectory is a reminder of how much we still do not know. Measuring the precise motion of an object 2.5 million light-years away is incredibly difficult. The Gaia mission is helping. By tracking the positions of billions of stars over multiple years, we are building a three-dimensional map of motion in our cosmic neighborhood. But there is still uncertainty in the measurements. And that uncertainty matters because it changes the entire timeline for the Milky Way's future. Will we merge with Andromeda in 4 billion years, or 10 billion years, or even longer? Will the merger be violent and fast, or slow and gradual? Will the Milky Way's spiral structure be destroyed quickly, or will it persist for billions of years longer than we thought? These are not just academic questions. They affect how we think about the long-term future of our galaxy. But here is what does not change. Even in the best-case scenario, even if Andromeda misses us completely on the first pass, the gravitational interaction will still reshape the Milky Way. Tidal forces will pull stars out of the disk. The spiral arms will be disturbed. The galactic structure we have mapped so carefully will change. Some stars will be flung out into intergalactic space. Others will be pulled into new orbits. The night sky for any civilization that might exist on Earth or elsewhere in the galaxy billions of years from now will look completely different. Andromeda, which currently appears as a faint smudge in our sky, will grow larger and brighter over millions of years. Eventually, it will stretch across the heavens, a spectacular band of light and dust. Tidal tails will arc overhead, streams of stars pulled out of both galaxies. The sky will be filled with newborn stars, blue and brilliant, clustered in regions where gas clouds collided and compressed. It will be one of the most beautiful and dramatic sights in the universe, a reminder that even galaxies are not permanent. They evolve, they interact, and they change. And over long enough timescales, billions of years, the merger is still likely to happen eventually. Andromeda is part of the same gravitational system as the Milky Way. We are bound together. The local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is a gravitationally bound system. Sooner or later, the two largest galaxies in that system will merge. It is inevitable. The only question is when and how. When it does happen, it will be the end of the Milky Way as a spiral galaxy. But it will not be the end of the stars, or the planets, or the possibility of life. Galactic mergers are common in the universe. The Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of colliding galaxies. These images show galaxies in various stages of merger, from the first close approach to the final merged elliptical. And what we see is that through it all, stars keep shining, planets keep orbiting. The individual star systems mostly survive intact. Yes, some stars get flung out into intergalactic space. Yes, the overall structure of the galaxy changes dramatically. But the stars themselves, and any planets orbiting them, are mostly unaffected. Life, if it exists on planets in the collision zone, might not even notice on a day-to-day basis. The changes happen over millions of years, too slow to perceive directly. But the night sky would change. Over millions of years, civilizations would see Andromeda grow larger and larger. They would see new stars being born in massive bursts. They would see the sky transform as the two galaxies merged. It would be spectacular, terrifying in its scale, but also beautiful. And that is the nature of this threat. It is not a sudden catastrophe. It is a slow, inexorable transformation. The Milky Way will not be destroyed. It will be transformed into something new. So we have looked at three threats to the Milky Way. False vacuum decay, which is theoretically possible, but so unlikely we can ignore it. Sagittarius A star, which is active right now and could transition into a quasar at any time. And the Andromeda collision, which is definitely happening but might not happen the way we thought. What ties all of these together is a simple realization. The Milky Way is not static. It is not a fixed structure sitting in space, unchanging for eternity. It is a dynamic, evolving system that has changed dramatically over its 13 billion-year history and will continue to change in the future. For most of human history, we thought the universe was unchanging. The stars were fixed points of light. The constellations looked the same generation after generation. The Milky Way was a permanent feature of the night sky. But that is only because human lifetimes are so short. On cosmic timescales, everything is in motion. Stars are born and die. Galaxies collide and merge. Even the universe itself is expanding, carrying galaxies away from each other at ever-increasing speeds. The Milky Way is about 13 billion years old. It formed from a cloud of gas in the early universe, about 800 million years after the Big Bang. That primordial cloud collapsed under its own gravity, spinning faster as it contracted, eventually forming a rotating disk. The first stars in the Milky Way were very different from the stars we see today. They were made almost entirely of hydrogen and helium, the only elements that existed in significant quantities in the early universe. These first-generation stars, called population 3 stars, were probably very massive and very short-lived. When these massive stars died in supernova explosions, they scattered heavy elements across space. Carbon, oxygen, nitrogen, iron, all the elements created in stellar cores through nuclear fusion were released into the interstellar medium. The next generation of stars formed from gas that was enriched with these heavy elements. And when those stars died, they added even more heavy elements to the mix. Generation after generation, the galaxy became more and more metal-rich, in the astronomical sense of the word metal, which means any element heavier than hydrogen and helium. Our Sun is a relatively recent star. It formed about 4.5 billion years ago, which means it is a late arrival in the galaxy's history. The gas cloud that collapsed to form the Sun already contained all the elements needed to make rocky planets and eventually life. But the Milky Way did not grow in isolation. It grew by consuming smaller galaxies. This process, called galactic cannibalism, has been going on for billions of years and continues today. The Sagittarius dwarf elliptical galaxy is being torn apart right now. This small galaxy, which contains a few tens of millions of stars, has passed through the Milky Way's disk multiple times. Each passage strips away more stars and gas, leaving long streams of debris that wrap around our galaxy like ribbons. Astronomers have mapped these streams using data from the Gaia mission. They can see the scattered remnants of the Sagittarius dwarf galaxy stretched across the sky. In a few billion years, those stars will be completely integrated into the Milky Way, and the Sagittarius dwarf will cease to exist as a separate entity. The Large and Small Magellanic Clouds, two small irregular galaxies visible to the naked eye from the southern hemisphere, face the same fate. They orbit the Milky Way at a distance of about 160,000 light-years, and they are slowly spiraling inward. Recent studies using data from the Hubble Space Telescope and Gaia suggest that the Magellanic Clouds might merge with each other first, and then the merged system will eventually collide with the Milky Way. When that happens, probably in about 2 billion years, we will gain another few tens of billions of stars. This process of growth through mergers is how all large galaxies form. In the early universe, galaxies were much smaller. They grew by merging with other small galaxies, building up mass over billions of years. Computer simulations of galaxy formation show this process clearly. Start with a distribution of dark matter in the early universe. That dark matter clumps together under its own gravity, forming what astronomers call dark matter halos. Normal matter, the hydrogen and helium gas, falls into these dark matter halos. The gas collapses, heats up, and begins forming stars. You get small galaxies, each one sitting in its own dark matter halo. These small galaxies are attracted to each other by gravity. Over time, they merge, forming larger galaxies, and those larger galaxies merge with other large galaxies, forming even larger ones. The Milky Way is the result of countless mergers over billions of years. We are not a pure, single entity. We are a composite, built from the remains of dozens or even hundreds of smaller galaxies that were consumed over cosmic time. Some of the stars in our night sky might have formed in galaxies that no longer exist. Their original homes were dissolved, their stars scattered and mixed into the Milky Way. And the process continues. Right now, the Milky Way is consuming smaller galaxies. In a few billion years, we will merge with Andromeda, the largest galaxy in our local group. And eventually, the merged Milkomeda galaxy might consume other nearby galaxies in the local group. This is the natural life cycle of galaxies. They grow through mergers, they evolve, they change. And understanding this helps us understand the threats the Milky Way faces, because these threats are not external catastrophes being imposed on an otherwise stable system. They are part of the natural evolution of the galaxy. The activity at the galactic center, Sagittarius A's star flaring and occasionally erupting, that is part of how supermassive black holes grow and how they shape their host galaxies. The Andromeda collision, that is part of how galaxies grow and evolve through mergers that reshape their structure and trigger new generations of star formation. Even false vacuum decay, if it were to happen, would just be the universe transitioning to a lower energy state. A natural process, even if it would be catastrophic for us. This raises an interesting question. Where does life fit into all of this? If the Milky Way is this dynamic, evolving, occasionally violent place, how does life manage to emerge and survive? The answer is that life, at least as we know it, requires stability over long timescales. You need a star that shines steadily for billions of years. You need a planet that maintains liquid water on its surface. You need an environment that is not constantly being sterilized by nearby supernova explosions or radiation from an active galactic nucleus. This is where the concept of the galactic habitable zone comes in. Not all parts of the Milky Way are equally hospitable to life. The galactic center is too violent. Supernova explosions are frequent. The density of stars is so high that close encounters between stellar systems are common, and the central black hole, when it is actively feeding, can flood the region with deadly radiation. On the other hand, the outer regions of the galaxy are too sparse. There are fewer heavy elements, which means fewer rocky planets. Star formation is slower. The environment is less rich in the chemical diversity needed for complex life. The galactic habitable zone is a ring-shaped region between these two extremes. It is located roughly between 13,000 and 33,000 light-years from the galactic center. Our solar system, at 26,000 light-years from the center, sits right in the middle of this zone. Here, conditions are just right. There are enough heavy elements to form rocky planets and support complex chemistry. But the environment is not so violent that life gets repeatedly sterilized. Star formation is steady but not overwhelming. Supernova explosions happen, but not so frequently that they are a constant threat. And we are far enough from the galactic center that even if Sagittarius A star becomes a quasar, we would probably be safe. This might not be a coincidence. If life requires these specific conditions, then life will naturally tend to emerge in the regions where those conditions exist. But even in the galactic habitable zone, there are challenges. The Milky Way is not a perfectly calm, stable place. The galaxy undergoes cycles of activity. Star formation rates rise and fall over tens of millions of years. The spiral arms compress gas clouds as they rotate, triggering bursts of star formation. The Sun's orbit around the galaxy takes about 225 million years. During that time, we pass through different environments. Sometimes we are in the interarm regions, the relatively quiet zones between spiral arms. Other times we pass through the spiral arms themselves, where star formation is more active and the density of gas and stars is higher. Some researchers have even proposed that the Sun's passage through spiral arms might affect life on Earth. When we pass through a spiral arm, we are exposed to more cosmic rays, more supernova explosions, and more gravitational disturbances. This could potentially trigger ice ages or extinction events. The evidence for this is not conclusive, but it is an interesting idea. It suggests that even out here in the galactic habitable zone, the galaxy's structure and evolution can influence conditions on Earth. And then there is the question of other civilizations. If the Milky Way is this dynamic and occasionally violent place, where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked during a lunch conversation in 1950, "Where is everybody?" The question seems simple, but it has profound implications. The galaxy is old, about 13 billion years. It is vast, stretching 100,000 light-years across. It contains hundreds of billions of stars, and we now know that most of those stars have planets. The Kepler Space Telescope found that roughly half of Sun-like stars have at least one planet in the habitable zone. Do the math, and you get tens of billions of potentially habitable planets in our galaxy alone. That is just in the Milky Way. There are hundreds of billions of galaxies in the observable universe. Even if life is rare, even if only 1 in a million habitable planets actually develops life, and even if only 1 in a million life-bearing planets develops intelligent, technological civilizations, there should still be thousands or millions of civilizations in the Milky Way alone. Some of those civilizations should be far older than ours. The Sun is a relatively young star. There are stars in the galaxy that formed 8 or 9 billion years ago, when the universe was less than half its current age. If life emerged on planets around those stars on the same timescale it took to emerge on Earth, there could be civilizations that are billions of years older than human civilization. What could a civilization do with a billion-year head start? Our technology has advanced from stone tools to spacecraft in just 10,000 years. Imagine what a civilization could accomplish with 1,000,000 times longer to develop. They should be everywhere. They should have spread across the galaxy. They should have built structures we could detect. Dyson spheres around stars, massive engineering projects, radio transmissions, something. But we see nothing. The galaxy is silent. This is the Fermi paradox. The apparent contradiction between the high probability that alien civilizations should exist and the complete lack of evidence for them. There are many proposed solutions to the paradox, and none of them are entirely satisfying. Let's walk through some of the main possibilities. Possibility 1. Life is rare. Maybe life is much rarer than we think. Maybe the jump from chemistry to biology, from non-living molecules to living, self-replicating organisms, is incredibly difficult. Maybe it requires such a precise set of conditions that it almost never happens. This is sometimes called the rare Earth hypothesis. The idea is that while planets might be common, planets that can actually support complex life are extraordinarily rare. You need a planet with the right mass. Too small, and it cannot hold an atmosphere. Too large, and it might be a gas giant or have surface gravity so strong that complex chemistry cannot develop. You need the planet to be in the habitable zone, not too close to the star where water boils away, not too far where it freezes solid. You need a star that is stable and long-lived. Very massive stars burn out too quickly. Very small stars can have violent flares that would sterilize nearby planets. You need the planet to have a strong magnetic field to protect against cosmic rays and stellar wind. Earth's magnetic field is created by the churning molten iron in its core. Not all rocky planets have this. You need plate tectonics to cycle carbon and regulate the climate over geological timescales. Earth's plate tectonics might be partly due to our large moon, which creates tidal forces in Earth's mantle. And speaking of the moon, you might need a large satellite to stabilize the planet's rotational axis. Without the moon, Earth's axis would wobble chaotically, leading to extreme climate swings that might prevent complex life from developing. You need the planet to be in the right part of the galaxy. Too close to the center, and you get sterilized by radiation. Too far out, and there are not enough heavy elements to form rocky planets. You need a giant planet like Jupiter in the outer system to act as a vacuum cleaner, sweeping up comets and asteroids that might otherwise impact the inner planets too frequently. When you add up all these requirements, maybe habitable planets are not as common as we think. Maybe Earth really is special, a perfect storm of favorable conditions that almost never occurs. If that is the case, then life might be incredibly rare. There might be only a handful of life-bearing planets in the entire galaxy, or even fewer. But this does not fully solve the Fermi paradox. Even if complex life is rare, with hundreds of billions of stars in the galaxy, rare does not mean unique. There should still be others out there, somewhere. Possibility 2. Intelligence is rare. Maybe life is common, but intelligence is rare. Maybe the leap from simple, single-celled organisms to complex, intelligent beings capable of building civilizations is extraordinarily unlikely. On Earth, life emerged relatively quickly. The oldest evidence of life dates back to about 3.8 billion years ago, just a few 100 million years after Earth's surface cooled enough to support liquid water. But for most of Earth's history, life was simple. Single-celled organisms dominated for billions of years. Complex multicellular life only emerged about 600 million years ago. And even then, it took another 500 million years for intelligence to develop. Maybe that is typical. Maybe most planets that develop life stay at the microbial stage forever. Maybe the jump to complex multicellular life requires a series of unlikely evolutionary steps. On Earth, complex life required several key innovations. The evolution of eukaryotic cells, cells with a nucleus, happened about 2 billion years ago and might have been a fluke. Eukaryotic cells probably evolved when one cell engulfed another, and instead of digesting it, the two cells formed a symbiotic relationship. The engulfed cell became the mitochondria, the powerhouse of modern cells. This might have only happened once in Earth's entire history. Every eukaryotic cell on Earth, every plant, animal, fungus, comes from that one original merger. If that kind of event is extraordinarily rare, then most planets might be stuck with simple bacterial life forever. And even once you have complex life, intelligence might be rare. Evolution does not automatically lead to intelligence. For billions of years, complex life on Earth did fine without it. Intelligence is energetically expensive. Big brains require a lot of calories. They only evolve if there is a strong selective pressure for problem-solving abilities. On Earth, intelligence seems to have evolved multiple times independently. Dolphins, elephants, primates, even some birds like crows and parrots show sophisticated intelligence. But only one species, humans, developed the kind of abstract thinking and tool use that leads to technology and civilization. Maybe that is typical. Maybe most planets with complex life develop various forms of intelligence, but never quite make the leap to technological civilization. If intelligence is rare, then even if microbial life is common throughout the galaxy, technological civilizations might be incredibly sparse. There might be only a few per galaxy, or even fewer. Possibility 3. The Great Filter. This is one of the more disturbing solutions to the Fermi paradox. Maybe civilizations do develop regularly, but they do not last long. Maybe there is some barrier, some challenge that most civilizations fail to overcome. This barrier is called the Great Filter. The idea is that in the progression from non-living matter to spacefaring civilization, there is at least one step that is extraordinarily difficult. A filter that eliminates most attempts. The question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, if it was the jump from chemistry to life or from simple life to complex life, then we have already passed the hardest part. The galaxy might be full of simple life, but complex, intelligent civilizations are rare. We are special for having made it this far. That is actually the optimistic scenario. But if the filter is ahead of us, then we have a problem. Maybe civilizations regularly develop to about our level of technology, but then something happens that wipes most of them out. Nuclear war, environmental collapse, a pandemic, artificial intelligence that goes wrong, self-replication nanotechnology that gets out of control. Or maybe it is something we have not thought of yet, some existential risk that becomes apparent only when civilizations reach a certain level of technological development. If the Great Filter is ahead of us, then the silence of the galaxy is not just a mystery, it is a warning. It means that most civilizations do not survive long enough to spread to the stars. And we might be facing the same fate. This possibility is why some scientists take existential risks very seriously. If the galaxy should be full of civilizations but is not, maybe it is because those civilizations destroyed themselves. And maybe we are about to do the same. But in the context of the threats we have been discussing, there is another possibility. Maybe the galaxy is more dangerous than we think. Maybe civilizations do arise, but they get wiped out by events we have not considered. A nearby supernova could sterilize a region of space tens or even hundreds of light-years across. A gamma-ray burst, if it were aimed at us, could strip away Earth's ozone layer and flood the surface with deadly ultraviolet radiation. A quasar outburst from the galactic center, if the jets were oriented differently than we expect, could irradiate huge swaths of the inner galaxy. Or maybe civilizations just have bad luck. Maybe they emerge on planets in regions of the galaxy that are less stable than ours. Maybe they face more frequent extinction events. We do not know, but the silence of the galaxy is one of its deepest mysteries, and it is a reminder that even if life can emerge, even if intelligence can develop, long-term survival is not guaranteed. The threats we have discussed tonight, Sagittarius A star waking up, the Andromeda collision, even the remote possibility of false vacuum decay, they are all part of a universe that is not designed for our comfort. It is beautiful, it is awe-inspiring, but it is also indifferent. And that makes our existence all the more remarkable. Against all odds, on a small planet orbiting an ordinary star in a quiet corner of the galaxy, life emerged. And that life eventually developed the ability to look outward, to build telescopes, to study the universe and try to understand its nature. We are the universe trying to understand itself, and that is extraordinary. So what does the future hold for the Milky Way? Over the next few billion years, the galaxy will continue to evolve. Sagittarius A star will continue to feed, occasionally flaring as gas clouds fall toward it. The Sagittarius dwarf galaxy will be completely dissolved, its stars fully integrated into our galaxy. The Magellanic Clouds will spiral inward and eventually merge with us. Star formation will continue. New stars will be born from collapsing gas clouds. Some of those stars will be massive and short-lived, exploding as supernova within just a few million years. Others will be small red dwarfs that will burn slowly for trillions of years, far longer than the current age of the universe. Planets will continue to form. Some of those planets might be in the habitable zone. Some might develop life. And maybe, just maybe, some of that life will develop intelligence and technology, and they will look up at their night sky and ask the same questions we are asking. In about 4 to 10 billion years, depending on how the measurements of Andromeda's motion play out, the Andromeda collision will begin. The two galaxies will approach each other, their gravitational fields reaching out across millions of light years. The first close encounter will be spectacular. Tidal forces will pull stars out of both galaxies. Long streams of stars will stretch between the two spirals. Gas clouds will collide, triggering massive bursts of star formation. If you could somehow watch this process at a highly accelerated rate, it would look like a slow-motion dance. The two galaxies would approach, pass through each other, separate, and then come back together. Each pass would be a little closer. Each collision would strip away more energy from their orbits. Eventually, after billions of years, the merger would be complete. The spiral structures would be gone, dissolved by the chaos of the collision. The stars would be redistributed into a giant elliptical galaxy. The two central black holes would spiral together and merge, releasing a burst of gravitational waves that would ripple across the universe. And the result would be Milky Way, a new galaxy, larger than either the Milky Way or Andromeda, but fundamentally different in structure. But even that is not the end of the story. Milky Way would continue to evolve. It might consume other galaxies in the local group. Star formation would continue for a while, fueled by the gas compressed during the merger, but eventually the gas would be used up. Over tens of billions of years, star formation would slow and eventually stop. The last massive stars would die in supernova explosions. The smaller stars would continue to burn, but no new stars would be born to replace the ones that died. Eventually, trillions of years from now, even the smallest stars would burn out. The galaxy would become a collection of dead stellar remnants. White dwarfs, neutron stars, and black holes, all slowly cooling in the darkness. This is the far future of the Milky Way. Not a sudden catastrophic end, but a slow fade. The lights go out one by one until only darkness remains. But that is trillions of years away. For now, the Milky Way is alive. Stars are being born. Planets are forming. And on at least one of those planets, life has emerged that can look up and appreciate the beauty and wonder of it all. So let's bring it all together. We have talked about 3 major threats to the Milky Way, and we have ranked them based on their likelihood and their potential impact. This is the ultimate existential threat. If it happens, the Milky Way, the universe as we know it, everything would be erased instantly with no warning. But the probability is so incredibly low that it is essentially not worth worrying about. The universe has existed for nearly 14 billion years without vacuum decay occurring, and the physics suggests it will remain stable for far longer than that. It is a fascinating theoretical possibility, a reminder that the universe might not be in its most stable state, but practically speaking, it is not a threat we need to lose sleep over. This is a real, active threat. The supermassive black hole at the center of our galaxy is not dormant. The latest observations from the James Webb Space Telescope and the Event Horizon Telescope show that it is flaring constantly, feeding on gas and dust that drifts too close. If Sagittarius A star transitions into a full quasar state, consuming matter at a much higher rate and releasing enormous amounts of energy in jets and radiation, it could reshape the inner regions of the galaxy. Star formation could be suppressed. Regions near the galactic center could be sterilized. We are probably safe out here at 26,000 light-years, but the threat is real and ongoing. The monster at the heart of the Milky Way is awake, and we are living with it. This is the big one, and it is the one with the biggest twist. For decades, we were told that Andromeda would definitely collide with the Milky Way in about 4 to 5 billion years, merging the two galaxies into a giant elliptical. But the latest measurements of Andromeda's motion show significant tangential velocity. Andromeda is not heading straight for us. It is approaching at an angle. This introduces real uncertainty. A direct collision is still the most likely outcome, but a grazing encounter is possible. In the most optimistic interpretation, a near miss cannot be ruled out. The exact timeline and nature of the collision are now uncertain. It might happen in 4 billion years, or it might be pushed back to 10 billion years or more. The merger might be violent and fast, or it might be slow and gradual. But one thing is certain. Over long enough timescales, the Milky Way and Andromeda will interact gravitationally. Tidal forces will reshape both galaxies, and eventually they will merge. When that happens, it will be the end of the Milky Way as we know it. The beautiful spiral structure will be destroyed. The stars will be redistributed into a new configuration. It will be a complete transformation. But it will also be beautiful. Galactic collisions are spectacular events. They trigger massive bursts of star formation. They create long tidal tails of stars stretching across millions of light years. They are cosmic dances, played out over billions of years. And through it all, individual star systems mostly survive. The stars keep shining, planets keep orbiting. Life, if it exists, continues. So yes, the Milky Way faces threats, but these threats are not catastrophes to be feared. They are part of the natural evolution of galaxies in an ever-changing universe. The Milky Way has survived for 13 billion years. It has grown through mergers, evolved through countless generations of star formation, and adapted to changing conditions. It will continue to evolve, and eventually it will merge with Andromeda to become something new. But right now, in this moment, the Milky Way is here. It is our home. It is the structure that gave birth to the Sun, the Earth, and us. Every atom in your body was forged in a star. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it came from stellar nucleosynthesis, from stars that lived and died billions of years ago and scattered their material across the galaxy. We are not separate from the Milky Way. We are part of it. We are the galaxy looking at itself, trying to understand its own nature. The threats we have discussed tonight remind us that nothing is permanent. Not stars, not galaxies, not even the universe itself. Everything changes, everything evolves. But that does not make existence meaningless. If anything, it makes it more precious. We exist in this brief window of time, when the Milky Way is a beautiful spiral, when stars are being born, when life can emerge and flourish. Billions of years from now, the galaxy will look completely different. It will have merged with Andromeda. The night sky will be unrecognizable. And eventually, trillions of years in the future, the last stars will burn out and the universe will grow cold and dark. But right now, we are here. We can look up at the night sky and see the Milky Way stretching across the darkness. We can build telescopes and study its structure. We can map its spiral arms, image its central black hole, and predict its future collision with Andromeda. We are living in an incredible time. The tools we have now, the James Webb Space Telescope, the Event Horizon Telescope, the Gaia mission, they are allowing us to see the universe in ways that would have been impossible just a few decades ago. Every year brings new discoveries, new insights into how galaxies form and evolve, new understanding of the threats they face and how they survive. The Milky Way is not a static museum piece. It is a living, evolving system. It has a past, a present, and a future. And we are privileged to be here, in this moment, able to observe it and try to understand it. So the next time you look up at the night sky, remember what you are seeing. That faint band of light stretching across the darkness is not just a pretty sight. It is your home, seen from the inside. It is 400 billion stars, each one a sun, many with their own planets. It is a galaxy that has survived for 13 billion years, that has grown through countless mergers, that faces real threats but continues to evolve. It is a galaxy that contains at least one planet where life emerged and developed the ability to look outward and ask questions about its place in the cosmos. And that is extraordinary. Against all odds, in a universe that is vast and indifferent, we exist. We are here. We are asking questions. We are building telescopes and mapping galaxies and trying to understand the nature of reality. The biggest threats to the Milky Way are real. They are measurable. They are fascinating to study, but they are also reminders that we are part of something much larger than ourselves. We are part of a galaxy that is constantly changing, constantly evolving, facing challenges over timescales that dwarf human history, but that we can now understand and predict. And in understanding these threats, we gain a deeper appreciation for the fragility and resilience of our cosmic home. The Milky Way has weathered 13 billion years of cosmic evolution. It has merged with countless smaller galaxies. It has survived near misses with other large systems. It has regulated itself through cycles of star formation and quiescence. Through it all, conditions remained stable enough in at least one small region for life to emerge, evolve, and eventually develop the capacity to understand its origins. That is not just lucky. It suggests that galaxies, even as they face these dramatic threats, contain pockets of relative stability where complexity can grow. The future of the Milky Way is not one of sudden catastrophe, but of gradual transformation. Whether Sagittarius A star erupts tomorrow or in a million years, whether Andromeda arrives in 4 billion years or 10 billion years, whether the vacuum is stable or metastable, the fundamental story remains the same. Galaxies are living, evolving systems. They are born from clouds of primordial gas. They grow through mergers. They form stars and planets and perhaps life. They interact with their neighbors. And eventually, they transform into something new. The Milky Way will not exist forever in its current form, but the stars that make it up, the planets that orbit those stars, the atoms that make up those planets, all of that will persist in some form. Matter is neither created nor destroyed. It just changes form, recycling through the cosmos in an endless dance of creation and destruction. And maybe, billions of years from now, when the Milky Way has merged with Andromeda and the new Milky galaxy has settled into its elliptical form, there will still be pockets of stability. Regions where stars shine steadily, where planets orbit in stable zones, where life persists or emerges anew. Maybe civilizations in that future galaxy will look back at the ancient archives, if any survive, and learn about the time when their home was two separate spirals. Maybe they will study the same questions we are studying now. Why are we here? What threatens our existence? And how long can this last? The threats to the Milky Way teach us humility. They remind us that nothing is permanent, not even galaxies, but they also teach us resilience, because the Milky Way has faced threats before and survived. It will face threats in the future and adapt. And we, as temporary inhabitants of this galaxy, have the extraordinary privilege of being here during one of its most beautiful phases. The spiral is intact, the stars are shining. The conditions for life and consciousness exist, and we can look outward and understand what we see. That is the ultimate gift of these discoveries. Not fear of cosmic threats, but appreciation for cosmic beauty. The knowledge that we are part of something ancient, vast, and magnificent. Something that will outlast us, but that we can, for this brief moment, observe and comprehend. The galaxy turns, the stars shine, and somewhere in all that vastness, we exist, trying to make sense of it all. The Milky Way faces threats, yes, but it endures, and so do we, at least for now, and that is something truly worth celebrating. Each discovery we make, each measurement we refine, each theory we test, brings us closer to understanding not just the threats our galaxy faces, but the mechanisms that have allowed it to thrive for so long. The interplay between dark matter and normal matter. The feedback loops between black holes and galaxy formation. The chemical enrichment that makes rocky planets possible. These are not just academic curiosities, they are the processes that made our existence possible. The tools we have developed are remarkable. The James Webb Space Telescope peers back to the earliest galaxies, showing us what the universe looked like when it was young. The Event Horizon Telescope creates Earth-sized virtual instruments that can photograph the shadows of black holes. The Gaia mission maps 1 billion stars with precision that would have seemed impossible just decades ago. Each instrument answers old questions and raises new ones. And as we look forward, those questions multiply. Will we detect biosignatures on nearby exoplanets in the next decade? Will the Laser Interferometer Space Antenna hear the gravitational wave symphony of merging black holes across the universe? Will we finally solve the mystery of dark matter's identity? Will we detect a signal from another civilization, or will the silence continue to echo across the void? These questions drive us forward. They inspire new generations of astronomers, physicists, and engineers to build better instruments, develop better theories, and peer ever deeper into the cosmos. The threats to the Milky Way are real, but so is our capacity to understand them, to put them in context, and to appreciate the vast tapestry of cosmic evolution that has led to this moment. When you look up at the night sky tonight, you are seeing photons that have traveled for years, decades, or even thousands of years to reach your eyes. You are seeing the Milky Way as it was, not as it is. And in a very real sense, every observation we make of the cosmos is an observation of history, a glimpse into the past that helps us understand the present and predict the future. The galaxy continues its slow rotation, carrying us along at 500,000 miles per hour, while we stand seemingly still on this small rocky world. The black hole at the center continues its patient consumption of nearby matter, occasionally flaring as gas falls past the point of no return. Andromeda continues its approach, drawing ever closer on a trajectory that will, eventually, lead to one of the most spectacular events in our local corner of the universe. And through it all, we watch, we measure, we learn. We are the universe becoming aware of itself, consciousness emerging from matter, asking questions about origins and endings, about threats and transformations. That capacity for wonder, for curiosity, for the desire to understand, that might be the most remarkable thing in the entire cosmos. The biggest threats to the Milky Way remind us that nothing lasts forever. But they also remind us that while we are here, while the conditions exist for us to observe and understand, we have an opportunity and perhaps even a responsibility to learn as much as we can. To map the stars, to image the black holes, to measure the distances, to predict the collisions, to solve the mysteries. Think about what we have learned in just the last century. 100 years ago, we did not even know other galaxies existed. We thought the Milky Way was the entire universe. Now we know it is one galaxy among hundreds of billions, each containing hundreds of billions of stars. We have measured the age of the universe. We have detected gravitational waves. We have photographed black holes. We have found thousands of planets around other stars. The pace of discovery is accelerating. What will we know in another 100 years? What questions that seem unanswerable today will become textbook facts for future generations? What mysteries we have not even thought to ask about yet will become the great challenges of the future? Because billions of years from now, when the Milky Way has transformed into something new, the knowledge we gather today might be all that remains of this particular configuration of matter and energy that we call home. The spiral arms will be gone. The current stellar populations will have aged and died, but the data we collect, the understanding we achieve, that could persist in some form, carried forward by whatever comes next. So we keep building telescopes, we keep asking questions, we keep searching for answers, not because the threats to the Milky Way demand it, but because understanding is its own reward. Because the universe has given us this brief window of stability and consciousness, and we choose to use it to comprehend the cosmos that made us. The Milky Way will outlast us. The spiral will turn long after humanity is gone. But for now, in this moment, we are here. We are watching. We are learning. And that connection between the vast impersonal forces that shape galaxies and the small conscious beings that observe them, that might be the most extraordinary thing of all. We are stardust that learned to think. We are atoms from ancient supernovae arranged in patterns complex enough to contemplate our own origins. We are the Milky Way's way of understanding itself. And for this brief cosmic moment, we have the privilege of looking outward, asking questions, and piecing together the story of our galactic home. The threats we have explored tonight, false vacuum decay, the awakening of Sagittarius, a star, the coming collision with Andromeda, they are reminders of impermanence. But they are also reminders of connection. We are not separate from these cosmic processes. We are part of them. The same forces that shape galaxies also shaped us. The same laws that govern black holes also govern the atoms in our bodies. So when we study the threats to the Milky Way, we are really studying ourselves, our origins, our context, our place in the grand cosmic story. And in doing so, we honor the billions of years of cosmic evolution that made this moment possible. The moment when matter became conscious and turned its gaze outward to understand the universe that created it. Keep looking up, keep wondering, keep asking questions, because as long as there is someone to ask them, the story continues. Thank you for joining me on this journey through the biggest threats to the Milky Way. You are not just living in the galaxy, you are made of it. You are part of its story, a brief but meaningful chapter in a saga that spans billions of years and will continue long after we